Hi, I'm David.
And I'm William.
And our project for 611 this year was an acoustic levitator with control coming from a camera, which we can show on display. In general, our goal was to levitate a styrofoam ball in our acoustic levitator along one axis using sound, which comes off of an array, two arrays actually, of ultrasonic transducers. We have two general modes of operation. One where we show a virtual ball used for control on the display, and the height of the ball is controlled by buttons on the FPGA. In another mode where we use another styrofoam ball in real life as the control, and as we adjust the height of this real life styrofoam ball, we also see the levitated ball move as well. We will show you the virtual ball mode first, which is one of our stretch goals. To start, we reset the system with all switches off and put a ball into the levitator. Now it's in the levitator, we can turn on switches 1 and 2 to put it into virtual ball control mode. And as you can see on the display, we're able to track the ball, and there's our virtual ball, which is shown in purple as well. You can also turn on an extra switch here, which will show you the pixels passing filter. As you can see, the entire ball is in green, which is great because we're actually able to tune how well our filter is working by adjusting the intensity of these blue LEDs. Now that this is working, I can turn the controller on, which is switch 5, and then as I hit the buttons, the ball will move up and down with the virtual ball in real life. Let me make exactly what I'm doing. The switches correspond to the buttons I'm pressing. Right now I'm pressing up. If I press down, the ball will go down. And we can also see on the FPGA itself, we can also see the position of the ball.
Next, we will demonstrate how to control the height of the levitated ball by using a non-virtual ball, a ball in real life shown on the right. So as you can see, we're currently in real life mode, non-virtual mode, where the display is detecting both the levitated ball in red on the left and the real life target ball on the right in blue. In this mode, we are also able to display a number of different metadata onto the subsect display, including the Y coordinates of the two balls, or other pieces of information such as the phase, or even the X coordinate of the levitated ball. Furthermore, we are able to demonstrate that based on the location of the real-life ball, the FPGA turns on a light saying whether or not the real-life ball is above, below, or equal to the levitated ball. When it is equal, it displays blue. When the levitated ball needs to move down, it displays green, and when it needs to move up, it displays red.
Now we show exactly how this works in action. So first we put the ball into the levitator, we hit the control switch, and then the levitated ball will now follow the target ball. As you can see, as we move the target ball up and down, the levitated ball follows, and the LED turns blue exactly when they meet.
We structured our work into 3 large modules, one for computer vision and image processing, one for hardware control, and one for displaying onto the VGA. We write the camera data into a BRAM, which is read out at 65 MHz for the display. Pixels are read out for image processing, where we detect the target and levitation balls using an HSV filter. We do this by converting the initial RGB values into HSV, which are easier to manipulate and tune filters with. From this, we're able to use that to calculate the average locations of the balls, and also be able to approximate the radius of the balls from the number of pixels that pass HSV. Here's a demonstration.
We then use this data for a proportional controller on the ultrasound, which uses two 40 kHz square waves to drive each of the two sets of transducers. We then either use the relative positions of the two target and levitated balls or the switch inputs to calculate the relevant phase of the wave to control the position of the ball being levitated. On the display, we show the balls, and because we pipelined it and added registers accordingly, we can also show the pixels passing the filter at any given time. Combining the three modules of display, hardware, and computer vision, we're able to have an integrated system with ultrasound, camera, and display working together in parallel. Thank you.